How's everybody doing tonight? Looks like it's 6 o'clock. We might as well get started. Yeah, excellent. I see a lot of you are in good shape tonight. That's good. Okay, a couple people didn't answer up. Go ahead and give me a green circle if you can hear me. I want to make sure everybody can hear me. Timberland, you have a comment? Okay. So far, I haven't heard any of you. Somebody say something.
Hello, Professor.
Thank you. I appreciate that. Y'all are the quietest bunch that I've ever had, I think. Okay, so you had some homework. I'm assuming everyone got that done. I need you to send me an email. In the email text, make a note that says whether it worked or not. If it worked, we'll grade this thing quickly because that way we'll be able to check. Don't send me it worked and then have the program not work. That really ticks off the guys that do the evaluation of the thing for me. So send me that email, send me your file, the source file, that .asm file, and a comment in the text that tells me whether it works or not. And give you about a minute to get that done. That should be second nature for you to do now, sending text files. I hear the mail thing beeping across the room, so Tom's going to have tons of good fun tonight looking at your work.
And will we be getting feedback on any of these?
If you set up time for it.
Might be a silly question. How do we go about setting up time for it?
You just ask me after class. Probably won't get to do it this week because we have that exam coming up at the start of next week, but we can do some office hours after that. Okay, anybody still trying to sending it and having trouble? Mohammed? You have a question?
No, Professor. My computer is just a little slow. The other one.
Okay. Okay. Okay, give you another 10 seconds or so. After that, it'll be called late. Be thinking about whether you'd like to volunteer to explain your algorithm. Okay, everybody should have gotten that done by now. If you haven't got it sent in, you maybe should rethink computer science, or else, yes, you truly do have a slow computer, which is a reasonable thing. I had a slow computer once. It didn't last long. Robert, you volunteering to explain your algorithm?
Sure.
Okay, let me hear it.
Okay. Are you wanting me to kind of explain how it works, or like the actual code, or?
Nope, I don't want to hear code. I want to hear you explain how it works, what you're doing.
Okay. So it takes the key presses, and much like the previous two programs, it puts them together into one byte, and then it isolates those bytes to both represent a single digit in binary, and then we multiply the tens digit by 10 to get its representation in hex. And the way we do that is we multiply it by 2, and then we multiply it by 8, and we add those together for the distributive property of multiplication, which gives us the first hex digit. The second hex digit, 0 through 9, is the same, so we just add the two together, and then we output them.
Okay. Who's we?
Well, the program that we've written.
Programming you? Okay. Anybody else want to explain their algorithm? Mohammed?
Yes. So the way I did is we take the input, and the first input we store that into the memory location. It could be any memory location, and then whatever is in the accumulator, we rotate that to the left 4 times, and basically send that to the output port, which is number 2, in this case. And then we refresh our ready button, and then we take the second input, and the second input we store that into our C register. First of all, the first input was also stored in the B register, and the second input we take will be stored in the C register. And once we store that, we load the memory, the data we stored in the memory in the very beginning, and then we rotate that to the left 4 times, meaning multiplying it with 8. And then we move that back to the B register. We take the another input, meaning it basically does the math and also converts the decimal into hex. That next input rotates to the left, since we are multiplying by 2 this time. That is basically the main algorithm. And then we add B to the value we have in accumulator, and then we add C, which is our very last, the second decimal number we entered, since we are not really changing that decimal. And then when we press the another key, it basically just changes everything and shows us the hex value.
Okay.
Yeah.
Anybody else have any different algorithms they used? Robert, what do you need?
I'm going to take a guess. I don't think there is a different way to do this.
Okay. I've got some good coffee tonight. I've remembered to put the coffee in the thing. I had coffee the other morning, and I wondered why it tasted weak. And I looked at it when I got done. I'd forgotten to put the coffee in. All I had was some protein drink and some Sweet and Low in a cup with hot water. Thought it didn't taste very tasty, but nevertheless, I made my way on through it. I didn't want to waste the protein powder. Okay, so let's talk about, for some of you that did not get it done, the way to think about parts of the problem. First of all, completely abstract away the conversion problem. If we focus too much on worrying about the conversion, all the housekeeping around the edges is not going to get done. So let's think about the housekeeping from what the teacher showed us last time it needs to do. We start the program. We need to get a decimal digit. And we need to display that digit left justified so that it is in the left 4 bits rather than in the right 4 bits. Now, getting a decimal digit is going to involve us polling the ready bit. And when the ready bit goes on, getting the digit, moving it over 4 positions so it's ready to be displayed, displaying it, and saving it somewhere. To save it already shifted over to the left because we have to acknowledge keypad. Now we're going to do similar to that. We're going to get a decimal digit. We're going to display it without any left justification in combination with whatever is in A at that point for the accumulator, because that's where we're probably going to save it. And then, of course, we have to act the keypad. Now, magic happens. We wait for a key press. We display the answer. We act the key. Now, is that roughly the spirit of what needs to be done? Scott, what do you think?
Yes.
Okay, let me see if I have a DOS window open anywhere on the screen here. I do. So if I say simulate DRB, I think mine was DRB 11. Keypad comes up. We type our first number. Let's say we wanted to do 67. I type a 6. The 6 is displayed on the left. It's a decimal digit. Now I wait for a key press, which when I type the 7 appears on the right side. 6 is still there. And now any other key press should lead me to a solution of the problem. So 64 plus 3 is 67. So 1, 2, 4, 8, 16, 32, 64, 128. So 64 plus 3. Now, the only thing we didn't have in our algorithm when we wrote it over here is this business about magic happens. And hopefully you didn't go to the web and look up an algorithm. That would be so lame on your part. The right way to do that is to come up with a solution yourself. And hopefully you did that, and hopefully you didn't share your solution with other people, but I guarantee you somebody did. Guarantee it. But nevertheless, we need to think about how magic happens. So in this kind of high-level English here, Robert, I'd like you to re-explain to me what you're going to do.
For just the magic happens part?
Everything else is already there.
Okay. So we're going to take the first decimal digit And we're going to put it back to right justified. We are going to multiply it by 10. And we're going to then add it to the second digit.
So you're going to add it to the number that was originally on the right-hand side 4 bits.
Correct.
Okay.
And
Okay.
then I think that's it. Then you're going to wait for the key press and display the answer.
So your answer always fits in 1 bit or in 8 bits after that add. You never have a carry out of the rightmost nibble.
No,
Why not?
because of the way you multiply by 10. Do you want me to break that down as well?
Let's get all the details down so others can understand it.
Okay. So in order to multiply by 10, you take your first decimal digit. So we can probably just erase multiply it by 10 and replace it with this.
Okay.
So we're gonna rotate it. Oh, you know what? No, I lied. We didn't return it to right justified.
Take the first decimal digit and just add it?
No. So we're going to take the first decimal digit and we're going to divide it by 2 by rotating to the right.
I don't care how you do it. So divide by 2.
Okay. Store that answer. And then you're going to divide by 4. And you're going to add those 2 answers together.
Okay.
And that will then have multiplied it by 10, at which point you'll add it to the low order bits, and then we're done.
Okay. Anybody have any polish they want to put on that algorithm? Nobody? Okay, what's the big O time for this particular algorithm?
Constant. Well, assuming that you're getting your inputs immediately. So while you're waiting, you're looping, but beyond that, it's just one shot.
Yeah, then we're looking to talk about this little piece of the algorithm here, where you have both the digits already. Would this run in some longer time if we had 3 digits to add rather than 2 digits to add?
Yeah, likely would. Oh.
If we said build a 3-digit decimal number and add it to another 3-digit decimal number, would this algorithm grow? Would we repeat any of this multiple times?
No, I don't believe so.
So we'd only do something to the tens digit. We wouldn't do anything to the hundreds.
Oh, no. Yeah, you're right. Okay. So it would be O to the N.
Okay. Anybody have any questions about that directed toward Robert? Okay, we'll save this. Magic happens. Okay, so we have some code, and everything else here we pretty much have to do. We did skip one thing in this part here where we need to save the digit, because if we don't, when we act the keyboard, we'll wipe it out because it was in A. So there's a save needs to be in here. Okay, let's look at the code that I'm running here so we can see a slightly different way to do the problem. Let's see, do I have that open? I don't think so. Okay. So we'll read the code as we go along here and see if we can decipher what's going on. We're clearing out the accumulator and outputting it so that we start with a fresh display. We will anyway, but it's a good practice if we ever put this in a loop. Now we poll by getting the register that has the ready bit in it. We look at the ready bit. If we don't have a character yet, if the ready bit's not on, we go back and do this again. Keep this in mind as being a terrible way to have to get a key, because we can't do any other work except wait for the key to arrive. So we'll solve that on machines later when we get interrupts, but this is a terrible thing. But in the design, that we could do it in passing. But fortunately, in this program, there's nothing you can do till you have the numbers anyway. We'll then input the number, shift it 4 positions to the left. We'll then move it into the B register to save it. We'll output the value that they typed in. We'll prepare for the acknowledgement, which wipes out A, and we'll acknowledge having seen the character. Keyboard unlocks. Same thing. We sit here waiting for a key. We get the key. It's in the accumulator, so we OR it with B. So now we have the 2 digits in the right places within one number in the accumulator. We save the accumulator in B, output the accumulator so we can see the whole 2 digits we're going to be working with. It's saved in B, remember. So we can clobber A, and we can output the acknowledgement bit. Now, we input, waiting for a key. We test for it. We keep going. Now, notice in this case, we're not going to get the key. And since the program's not going to repeat, we don't even need to acknowledge it. We can leave the keypad locked. It doesn't matter. We may leave it locked. We may not. So far, everybody, give me a green circle if you see what's been going on there. Okay, now magic happens. We pick B up again and put it into A because now we have the answer, the correct answer in A. We store the accumulator, which is our decimal number, at the location called offset, which is right here. We now execute an instruction which begins 3A, 80 offset. What is a DB instruction? Scott?
Define byte lets us literally define bytes for whatever purpose.
Yeah, but what's the 3A?
Load accumulator.
I asked the wrong question. Load accumulator. So we're going to load the accumulator from 8,000 and whatever that decimal number is. We're going to output that because that's the answer. And then halt. What did he say? What's at 8,000? Well, at 8,000, we have a table. The table repeats itself every 16 and has numbers in every one of the first 10 positions. We simply pre-compute all the answers. We're going to use less than 256 bytes. We've got, what, 32K or 65K of memory. It's not going to take any space. So we simply set the offset to be the decimal offset into this table. We go get the answer, we display it, and we're done. So a different way of thinking about the same problem. Okay, give me a green circle if you sort of see what's going on there. Okay, Dante, what's your question?
So yeah, I just didn't. If you could just explain that one more time for me, I just didn't
You're gonna have
clock
to
that.
talk up in your mic. I can't hear you.
I didn't really understand it. Yeah. So it's where. Yeah, I don't know.
Okay. So we're using this table to contain the numbers. So if we look in the table, at location 0, we get a 0. 1, we get a 1. 2, we get a 2. 3, we get a 3. 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, 9, 9. Now, if we get a 10, the decimal number 10, we don't want to look here at 0A. We want to look at table entry, even though it's base 16, 1, 0, which would be right here. And we have the number 10 stored there. So by using the decimal numbers to reference a hexadecimal table and just simply dummying out any values that we can't specify anyway. Remember with our program, let me run it again here. The biggest number we can produce is the number 99. And when we find out it's a 63. 6 times 16 is 96, plus 3 is 99. So we would expect to find in our table down here at the 99th entry, where the hex value, this is 99 in hex, is the number 63, which is the hex value we want for decimal 99.
Okay, yeah, that makes more sense. Okay, thank you, Professor.
Okay, that may not be completely clear. You'll have to think about it a little bit. Robert, you have a comment?
Did you just invent arrays?
I don't think so. I think that, remember in the SAP too, it doesn't do these easily, but last class, we very craftily figured out a way to do that, didn't we? Remember we were digging A, B, C, D? It's the same problem.
I just made the connection though that that's what this is. You're building an array.
If this were in a high-level language and you had a compiler that was any good, it would generate this code for us. Because it already knows what all the answers are. It's not going to make you compute it every time. Now, is this answer better than your answer? The answer is no. If yours does what the spec said, it's fine. And I'm especially happy with it if you didn't copy the algorithm from somewhere and if you didn't pass it on to anybody else. That would make me very happy. Not even going to ask because I'm going to believe you didn't. You know, that you made the algorithm up yourself and that you did not pass it on. Don't tell me if you didn't. Okay. Anybody have any other questions about that? This is just a different approach to the same problem. guess we're done with that for now. Okay. Yeah. Another question, Robert? Or is your hand still up?
Yeah. So does offset, does it have a place specifically in memory that it's stored, or is it just in line with the other instructions?
It's the address wherever we are right at the moment. All the
Okay.
labels, just like start, that's address 0. Done, when we have done as a label, it's just whatever address we happen to be at that moment, it's assigned to that label. Doesn't take any more space, doesn't take in an address, but it gets one for itself.
Okay.
Same thing happens with the DB statements, but they take up a byte after you've taken the address and given it a value, the label and given it a value. Good question, though. Very good question. Okay, shall we move ahead? Everybody remembers, let me look at my notes here. I was so excited to have, 20 people here. Everybody remembers that on Wednesday, November 17th, we have our next exam. That's next week, a week from today. And the focus is going to be on the SAPs, the 8085 and the 8088, but it will have things about bus architecture, programmable logic, HDLs, any of the stuff that we did those last couple of weeks before the last exam, because we didn't put those on the last exam. Also, because the material is cumulative, make certain that you've reviewed a lot of the other things. I will ask you, by the way, on Monday night, if you think we should have a review on Tuesday. I don't think we're going to need it, but I'll ask on Monday to see if anybody wants one. I would not let that slow you down from studying, because the material we cover on Monday is unique to itself, and it will take time to study between Monday and Wednesday just for that material. Mohammed, you have a question?
Yes, Professor. Are we going to have a question where we will have to write a program like similar to our homework?
It will not be as long or complicated if you do, because we're still going to try to keep the test time within the class period. But yes, you very well might. Now, if you turned in a non-working version of the thing or didn't turn something in, your exam will contain additional material that the people that have demonstrated they already know it don't have to do. So some of the tests will be a little dicier than others, and may be a little more thorough in your needing to see your knowledge of something. So you know whether you turned in an answer or a correct answer. Okay, let us move ahead. The next processor we want to take and look at is going to fix a couple of the problems we have with the SAP2. Who can tell me what those 3 problems are? Sue, what are at least one of them?
So no pointer.
Okay, somebody else give me another one.
No.
Scott?
No carry bit, or no carry.
No carry flag, yeah. Okay, and a third one, Patricia?
No nested calls.
Yeah, I would think those are the big 3 that we really encounter in the SAP2. The SAP3 fixes all 3 of those. And then the SAP3, turns out, is actually a watered down version of an Intel 8085 chip, which fixes a couple things with the SAP3, which we haven't talked about its problems yet, but it has a couple that we fix with the 8085. So we'll kind of talk about this. Anything I say about the SAP3 is probably true about this processor as well, but there'll be things about this that are not true about the SAP3. So we'll kind of work our way slowly into this because it is a different architecture. And while the SAP2 just kind of loosely was based on the SAP1, the SAP3 is pretty strongly based on the SAP2. So things we know now still apply. And we're going to want to pay attention to those as we go along. This is a chip for the SAP3 showing what it attaches to externally on its pins. It's a 40-pin chip, number 1 to 39 or 29 down, or 1 to 20, I guess it is, and then 21 to 40 on that side going up. VCC, the power, is on the right top. VSS, which is ground, is on the bottom left. We have an external crystal which runs for this processor at 4 megahertz. You want to remember that. Internally, that 4 megahertz is turned into 2 megahertz inside the chip. So the clock inside the chip is running at 2 megahertz. So we don't use a 555 timer and a flip-flop. Instead, we use a crystal oscillator, and we divide it by 2 inside the chip with circuitry in the chip. So this guy is operating at 2 megahertz, and he has a 4 megahertz clock coming in. We do have an output over here, which is called clock. This sends out a synchronized clock at 2 megahertz. So basically, the generated clock here is also pumped out on pin 37, so we can synchronize ourselves with other chips if we need to. The data lines run from D7 down to D0 and have unique pins to themselves. And the address lines run from A16, oh, this is actually 15. I can't tell if I actually typed 15 or 16 there, but it's 15 down here, down to 0. So there's 6 address lines. That tells it, like the SAP2, this has 65K or 64K, which is 536 bytes of memory. We know they're bytes because the data is 8 bits wide. So we got the number of address bytes we have, and we have the number of data bits we have. Notice that these are external to the chip. That means if we were to look at a diagram of this chip, we'd find out that the memory is not internal to it. Inside the chip, there is a memory address register, which supports these pins. There is a memory data register, and it also uses the addresses here to support the data pins. However, the actual data at the addresses are kept in a separate chip. Matter of fact, they're actually kept in 2 separate chips. One is RAM and one is ROM, and the addressing is done in such a way that they look like they overlap each other. And the data from 8000 up to FFF is RAM, and the lower memory, 0000, up to, well, I guess it would be 7FFF, is going to be ROM. So we want to keep that in mind because it's the same addressing the SAP2 did of its memory. But the memory here is kept external to the chip. We weren't sure in the SAP2 because the picture showed it internally. Now we have some other signals. We have 2 which are negative, meaning they're asserted when they go low. Only one at a time would go low. And during the time we're actually reading from memory, this pin goes low. During the time we're writing to memory, that pin goes high, or I should say writing from memory. We also have a pin that tells us whether the memory we're writing to should be the RAM and ROM or I/O addresses. So for input-output addresses, this is going to produce a 1. That 1 tells us that the addresses on these buses here are meaning to address some I/O port. It turns out that we have 256 I/O addresses. We can decide whether they're input, output, or both, and we can specify them as also being external to the chip. They are selected by setting this to a 1, meaning it's I/O, by, if we're reading from them, setting that to a 0, if we're writing to them, making this be a 1. And then the addresses in the low bits, we only use 7 bits for 256 bytes, will tell us which one of the I/O ports we're using. We have a reset pin that if we hold it at 0, the chip goes back to, it's the same as a clear pin, takes us all the way back to 0. First instruction is always executed on this machine from address 0000, just like it is on the SAP2. And I believe we've covered all the pins that the SAP3 has. The other pins that don't have labels on them, and some of these have secondary functions, on an 8085. So we'll see there's some additional things that happen on an 8085. And a fast 8085 would have a 6 megahertz clock with 3 megahertz internals. But a normal 8085 is just 4 megahertz with this. So basically, the SAP3 is an 8085 without some of the features. One of the features it doesn't have is interrupts, and the other features is some specialized instructions. So we'll talk about those when we talk about the instruction set. Anybody have any questions about the chip? Okay. Let's look at the programming model for this beast. Well, that's not very complicated. Let me blow that up a little bit. Because we know how an SAP one works, meaning we could tell you what the signals are on each of these boxes, and we know what the other boxes are that are necessary to move the instructions around or be the controller sequencer or whatever. Really all we have to talk about when we're talking about the programming model is how are its registers arranged? Are they 8-bit or 16-bit? And any other information that could be easily conveyed in a picture like this. And once you get experience with other processors, you can look and go, oh yeah, that's an 8085. So let's kind of get some scope on what these things are. First of all, these two longer boxes over, I'm in photos here, aren't I? Let me, open this in Paint so I can write on it. These are 16 bits long and always expressed, unless a 16-bit number is in memory, physically in memory, we always talk about it as though it's a big Indian number. If it's in memory, sometimes we have to put it the other way, depending on the processor. There are two registers which are 16 bits long by default here. The program counter and a register called the stack pointer. The stack pointer is going to help us solve the problem of nested call statements, as well as giving us some other places that we can store data. If you have a data structures class now, or you've had one in the past, you might also think of a stack as being something just like what you know it is. It's a last in, first out structure. We can put things in and we can get them out in the opposite order we put them in. So if I want to save some things, I could save A, then save B, then I could restore B and then restore A in that order because of the nesting. Now each of these registers over here are 8 bits wide. Why do these have to be 16 and these be 8? This is an easy question. Mikkel?
Is it so that PC could hold two registers memory at a time?
Well, it could, but for this particular question, I have a different answer in mind. Robert?
Because at some point we're going to have to be able to hold an instruction and data at the same time.
Well, why are they 16 bits long?
Well, because the instruction is going to take up a byte, as is the data that it's operating on.
We don't know that from here.
Oh, okay.
What does a programmer or program counter do? Scott?
It's going to cycle through the T states.
No, not in this case. Remember where the program counter was in the SAP2? It's up there kind of at the top left below the input outputs.
It's
What
a
did it
ring
always
counter.
contain?
The
What did it
address
always
of
contain? The what?
the address of the next instruction. So we have access to more instructions now.
Well, no way. The one on the program counter on the SAP2. Man, this is like breaking up with somebody and forgetting who they are the very next minute. Even I remember this, and I'm old. See if I've got a copy of that somewhere. You guys remember this thing? It has a program counter. It had 16 lines in and out of it. Why did it have 16 lines? Remember in the SAP1, the program counter only had 4 lines coming out of it. Why did it only have 4 lines? In memory, in a computer, the data, which might be an instruction or it might be data, lives at an address, right? How many addresses do we have? Mazu?
Is it 65, 536?
It is. And so what is this 16 then?
16 is the 2 to the power 16.
Which is?
65, 536.
Which is the number of bytes of memory we have. Therefore, the program counter needs to be able to point at every byte of memory. The stack pointer has 16 bits also, so maybe the stack can be anywhere in memory. If this was only 8 bits, we could only point at 256 bytes of memory. We need to be able to point it everywhere. We don't know where the next instruction is going to be. Only our program will know. Following the same line of thinking, why are these 8 bits long? Sharon?
Sorry, Professor, I pressed. I wasn't sure about it.
Okay. Okay. Mikhail?
Is it because they have 2 to the 8 power bytes that they need to store?
You can store any of 2 to the 8th values. That's 256 different numbers could be stored in the accumulator. 0 to this. So if this can hold data and data is 8 bits wide, it needs to be the same size as the data. If we have 16 bits of addresses, anything that can hold an address needs to be 16 bits wide. That can't be hard to understand. Okay. So just like we had in the SAP1 an A register and a B register, and then when we got to the SAP2, we had an A, a B, C, and a temp, we have registers in which to store data, A, B, C, D, E, H, and L. There is an F register over here. The F register stands for the flags register. It's where we're going to store things like the 0 flag or the sign flag, and anything else this processor has. There's going to be the flags that be stored in a register all to itself, and we'll be able to access it with instructions that know about the flags register. So there'll be a whole set of instructions which work on 8-bit data, and they can manipulate the stack pointer as a 16-bit entity. Now, it turns out, as we were trying to solve the problem that we had on the other machine, that we need to be able to deal with pointers. If we have a register and it needs to hold an address, how big does it have to be? Scott?
To hold the literal address, it would need to be 16 bits wide.
Right, so all our pointers, if we're going to develop pointers, would have to be 16 bits wide. So what they did on the SAP3 and then again on the 8085 is they said that for some instructions, you can treat that pair of registers as a single register named B. You can take that set of registers, treat it as a single register called D. Now, only some instructions. If you use D on another instruction, it's only talking about D. But on these special instructions, when you say D, it's taking D and E together to be a 16-bit number. And this one right here can be taken as H. Now, these don't particularly stand for anything right now. The H actually does, is like the F stands for flags and A stands for accumulator. But B, C, D, and E don't really stand for anything. And we'll come back to what these actually stand for when we get a little more under our belts. So if we come up with an instruction, so I'm going to make one up, the I-16 instruction, and we say, for whatever reason, we want to deal with register D. This instruction is using both D and E as its operand. We would never use a 16-bit instruction and say C, E, or L. Now, there's a couple special cases where we take the 8-bit accumulator and the 8 bits of flags. I think I didn't say 8 bits down here, but it's 8 bits. And there's special instructions that operate on the pair of those as though they were 16 bits wide. When they do, the name of them is not A, it's PSW, which stands for Program Status Word. It's the status of the current program because it knows where we are and what the current flags are. So there'll be some instructions that use the PSW that are 16, because this is 16 bits wide, but really all it is 8 bits of the accumulator pressed up against 8 bits of the flags. Any question about this architecture picture? So we expect there's somewhere in this thing to be the equivalent of a W bus. The W bus has to be 16 bits wide. Data has to be moved in the right 8 bits. All of these are 8 bits wide. If we ever have to move the pair like this, we would need to use all 16 lines of the bus. The register that contains the next instruction is the program counter, just like it is in the others. And when we load a value or instruction in, we put it in the instruction register. The opcodes for this machine just like the SAP2 are 8 bits wide. Instructions may be multiple bytes long, just like they were in the SAP2. Okay, I'll hang that around for a second. This we can get rid of. We have pointers because we can treat 16-bit data registers. We can take the 2 8s, press them together. We could treat it as though it's an address if we have an instruction that knows how to use that address. We have lots of room for flags. And yes, in fact, we're going to implement a carry flag, which takes care of handling when we carry from 8 bits over to the 9th bit. The stack will allow us to handle the nested calls. So let's talk about stacks for a second here. If I can find my whiteboard. So just mapping memory from high to low here. We're going to split our memory in the middle. We're going to start at 0, 0, 0, 0. This is read-only memory down here that we have to program with a programmer. That's where our data program will live. Top byte of it is at 7, F, F, F. Very similar to the SAP2 at this point. The RAM, which sits in the next area up here, starts at 8000 and ends at the top at FFFF. Now, the lowest part of memory, other than 0, here's byte 0 all to itself, consists of things having to do with interrupts. Let's put INT. This exists on the 8085, but does not exist in the SAP3 because it doesn't have interrupts. The first address is the address we go to upon reset. We don't have to program it, but it immediately jumps to the first byte of our program. So our program is in here. So our program lives there. Now, if we were using a compiler, this area up here would either be empty or it would be filled with libraries. We won't have any libraries for our stuff now, but we may in coding some other machines. So we just be aware that's where they would live. They'd be hardwired in to the fabric of the ROM. Now, RAM is where we store our variables going this direction. Every time we store a variable, it gets the next highest address. In the SAP2, we reserve the top 2 bytes of memory to be the place that we store the return address after we do a call. On this machine, we're going to initialize the stack pointer to point at the top. So we're going to write things on the stack going that direction. So even though it's physically lower on the page, this is the top of the stack. It grows from the bottom down here. As we add items toward the top and then shrinks back again. If we ever fall out by going past this, then we're going to wrap around to the beginning and we'll get a stack overflow. Actually underflow in that case, or overflow depending on which way you're looking at it. Same thing as if we try to read something on the stack where the top of the stack is not there, we'll get bad data. Whatever the last thing here was will be given to you. There's also something that in many systems, let's say you're logging in and they're saving your password on the stack. And then they remove that from the stack. Well, your password stays in memory. So somebody could write a variable that came from here down far enough to look at your password. That bug's been fixed on most things like Windows systems, but it still exists in a lot of pretty weak security systems. You got to be careful about what you put on the stack and then go back and erase critical things if necessary. So the way a stack works is we're going to have a couple operations. First of all, on this machine, we always push or pop it's always 16 bits. The main operations are push, which puts something on the stack, and pop, which removes it from the stack. Now, if I had registers B and C, this is a 16-bit instruction, so I could say push B. There's the H in it. Think of this as the high order byte, the low order byte. It'll push the high order byte first. So B, let's assume the stack is at the initial position here. It'll push B onto the stack. Then it'll push C on the stack. And now the pointer in the top of the stack will be right there. But what I want you to notice is as you're looking at memory, as the addresses get bigger, you get the low byte before the high byte. So when we're using 16 bits of data and we have it in memory, what type of indenness do we have on this processor? Robert?
Little.
Right, it's a little indent machine. We push the high byte first on the stack, but because we have another byte to write and it's the low byte, in memory, the low byte comes before the high byte, which is exactly what little indent looks like. And if I think about it next class, when I'm giving you a little information about the processor we're using, I'll explain where little and big indent actually came from in computer science. We know it came from literature from Gulliver's Travels, but I'll explain why we use little indent on many, many Intel processors. So this is the way if we popped it off, again, we'll do the opposite. This has got to move 16 bits, but each of these are 8. So C will come off first, go into the low half. B will come off next. It'll go into this part. We've now assembled a 16-bit number from little indent back to big indent. We use, in that case, pop some register. And again, it has to be a 16-bit register. And the only 16-bit registers on this machine that we know about so far are the program counter, the stack pointer, or SP, the B register, the D register, the H register, and what's the other one? Patricia?
PSW.
Yeah, the PSW, the program status word. So it's important to remember. Now we have two other things that happen for us. If we do a call, some address, when the call occurs, it automatically pushes onto the stack the address of the next instruction. So we call, we get an address pushed. If we call again before we return, we get it pushed again. Pushed again. We can add lots of it. We can call inside a call, inside a call, inside a call. Plus we run out of stack space. When we do a return, it will take the address that's on the stack and pop it off into the program counter. And remember, it's the thing that's the next address after the call, so we'll smoothly discontinue right afterwards. We've solved that problem. This is no longer a problem. This is no longer a problem. We haven't really talked about carry yet, but one of the things I did want to talk about is I want to talk about that flag register and talk about what it has inside of it that are useful. Let me just draw it here. So this is bit 7. This is bit 0. This is the flags. We only had 2 of them in the SAP2. But in here we do a little better. The sign flag is in the left position. This is the thing that tells us for the number we currently have set the flags for, meaning not all instructions set the flags, but if one did, if the value had its leftmost bit turned on, it potentially is a negative number, so turn this into a 1. If it's a positive number, meaning this is a 0 when the flags are set, then this would be a positive number and this sign would mean it's positive. Now, it might not really be used that way, but that's what we're going to handle it as. The next flag we've seen before is the 0 flag. If the instruction we're using at the moment sets the flags and it turns that flag, that bit or I should say turns the bits in the register we're looking at completely to zeros, this bit will get set. If any of the bits are on, this bit will not get set. Now, for some instructions, they know, for instance, we have a new instruction called add with carry. What add with carry does is it takes in A and B and the carry bit and adds them all up, produces a sum and a carry out. Now, obviously, in the first position, we don't have these things, but as you're moving along, and if you're using the carry, it's going to generate a carry bit for you, and you can make use of it in the add instruction itself. Our regular add in our world previously did not produce a carry. May now, we'll have to see. But in any event, the carry flag, which we'll just call CY over here, sits in the low order bit. Now, additionally, we have two other flags that are very uncommon to use, but we have them anyway. This bit, the P bit, which stands for parity. This tells us whether it's even or odd parity. And right now, I don't remember whether on means even or means odd, but we can look that up if we need it. The other thing we have is something called the auxiliary carry. Sometimes you find it useful to work with decimal numbers inside of an 8-bit binary number. The encoding for that is called binary coded decimal. And without knowing it in that last assignment, we were really doing it. We were putting in here a binary coded decimal digit, so it's just a decimal digit. You know, we want the number 6, so we'd have 0, 1, 1, 0. We want the number 9 over here, we'd have 1, 0, 0, 1. Each of these is a decimal digit. Now, wouldn't it be nice if when we added two of these binary coded decimals together, if we knew if this 4 bits overflowed, meaning it became 10 or bigger? Because if it did, we really needed to add the bit to this part over here. That's exactly what auxiliary carry does. Anytime we get a bit from here to here, meaning we had an overflow, auxiliary carry will be set. So for the, I think there's 2 instructions that do binary coded decimal on this machine, but that could be handy if you needed it. And of course, if this one overflows, regular carry will tell us about that. So that's just something even beyond our imagination, but in any sense here, we fix the fact we have no carry flag. So the SAP3 fixes those 3 items. It also, we're going to see down here, if we make it an 8085, it's going to fix a couple extra things that are wrong with the 8083. In particular, one of the things is binary coded decimal addition / subtraction. We just saw that it knows how to fix that with an instruction. Whether that's on the SAP3 or not, we don't know at this point. We'll have to look at the instruction set. But it's certainly on the 8085 because it's in the register. The other thing is interrupts, which are definitely not on the SAP3, but are on the 8085. And they'll keep showing their head where we care about them. And there actually is another register, which is 8 bits long, which is the instruction register that I'm not going to talk about with the SAP3. Also, we're not going to lay it out because we're not going to spend a lot of time talking about interrupts on this machine. We're going to acknowledge that they're there, but we're not going to spend a lot of time because we're going to definitely spend a lot of time in 2 weeks when we start using our ATmega 328P chips. You're going to want to, really, by the way, everybody remember those are, you need to have those the class after the test. So, which will be, I think, the only class we have Thanksgiving week, that Monday night. We'll have to check all those things, but make sure you've got that. If you haven't ordered it yet, get it ordered and make sure you've got it that night. Okay, so let me put this out of the way. Let me double check here that I only have SAP 3 things laying out. I do. So any questions so far about the architecture? Okay. Now, if I pull up the data sheet for an 8085, which is made by Intel, we'll talk about how that fits into the big plan of things. Let's look at some of the features that it has, and we can kind of also at this time talk about which ones the SAP 3 has and doesn't have. Remember, the SAP 3 is really just a transition machine to get us to this. Unlike most of the processors of the time, this particular processor worked with a single 5-volt power supply. We're working in the SAP 3 with the ability to operate at 4 megahertz as our main clock. But these were the 8085 speeds, and you buy an A, B, C, D model, something like that, to get the various speeds. We're not too worried about that because we're not really going to be running one, and we would be assured that they would actually work. Notice that if you're not running the full 6 megahertz, you can get as much as a 20% power differential, which can be very good if you're running on batteries or in some of the places you could go. Then they give us some instruction cycle. We could compute those. But remember, this isn't kind of an average cycle for the T states because memory on these things actually talked about it very briefly last class when we were trying to write T states for the SAP2 about how memory is slow. Occasionally, memory has to keep the processor from advancing to the next T state while it readies the memory. We fixed it in the SAP2 by allocating 2 T states to it, even if we didn't need the second T state. But be aware that's something that is done. We'll talk about this compatibility with 8088s and what that means, or 8080s, in the next class. We have an external crystal, and we're generating the actual clock on chip here instead of having to have something external that does that for us. We do have a system controller, and the system controller allows us to handle other boxes in the off the bus. The deal with this is there really are 2 major kinds of things called microprocessor-like devices. One is called microprocessor, and the other is called microcontroller. Microprocessors tend to be things that you would find in like a laptop or a regular desk PC, whereas a microcontroller tends to be things that you would find in a robot, an AI machine, in something that did home automation, or maybe something that ran a printing press. So it's something that's going to do control. And internally, it's going to have devices built in more than you would normally have in the processor itself, where on this chip, it has to go off chip to get them and needs controllers. And there, the controller and the, for instance, serial in, serial out port are built on the chip. Because this is in here, we could just as well call this a microcontroller. They hedge their bets when they talk about it in the data, because at the point where this was done, really they hadn't resolved all of that. We have 4 vectored interrupts. One is non-maskable, meaning you can't get rid of it. So you could use it if you lost power, for example. And whatever power you have left could run you to a clean shutdown. We do have a serial in and serial out port built into the chip. We have the ability to do decimal, binary, and double precision arithmetic, not through anything I'm going to show you, but through the ability to use a coprocessor. We have direct addressing. We already saw that up to 64K. That doesn't mean we couldn't go further. We could, but we'd have to use an external memory controller and jump through some hoops to make it happen. So we obviously could read about it. We won't. But notice this chip has a lot more things filled in. The other one didn't. But if you check all the pins, it does have that they'll match. On the left-hand side is the same thing as the diagram we've been looking at with the W bus. It just seems, or doesn't seem, it just is compressed in a little bit of a different way. And we've mostly extracted out here the architecture data that we needed to know. In here, you'll find the stack pointer, the program counter, the 3 registers. What you won't find here are the flags, the accumulator, and the temp register, just like the SAP2 that they really use when they're using the ALU. So this is kind of another way you can run your eyeballs over this picture, or the picture I gave you, it stands with this. I didn't get a copy of this for you if you want a copy. I just downloaded this from a company called Jameco. Let me give you the URL of this in case you want to have it. Grab that if you want it. I'm going to give you some of the other things we have, but this one I didn't make a copy of. Give me a green circle once you have it. If somebody wants to post the link in chat so they can use that, that's okay too. Okay, while that's downloading, we'll move ahead. Okay, they go through all the pins and various things. I'm interested next in page 11, as I recall, where there's a timing diagram for the 8085. Now, this is not unlike what we would find in the SAP3. At the top, we have the clock, low to high, low to high, low to. So it's the same phase as the SAP1 and 2. Here's our T states: T1, T2, T3, T4, T1, T2, T3, T1, T2, T3. Notice, though, that these are qualified with something called an M state. So this is T1 and M1, T1 and M2, T1 and M3. And just for a generic instruction, notice that the high order address, all during M1, is put on the bus. Notice in here that the program counter is going to put some piece of the data in here, but we're also going to actually get the data from the memory, which is the instruction, during this part of the thing, using these data lines. So while we're holding the address line and we have some data information in here, notice the dashed line. That means that the memory could put up a fight. If we have real slow memory, we might slow down for a while and not get the next clock tick until the memory has actually gotten the data ready. We have some other signals and things we haven't talked about before, but this is just kind of a general purpose thing to verify for us that yes, indeed, we had what we said last time is a much shorter M state. And in this case, T4 only occurs, if you notice, if we ever extend memory. Address latch enable will signify entering the next memory state. If I scroll on down from this, we get all sorts of data about the chip. Again, one of the reasons I didn't give this to you is that I don't want you spending a lot of time studying this sheet. It's a great reference, but don't try to be able to repeat all this because I'm not going to be testing you over it because this is specifically the 8085, not the SAP3. And while they're pretty much the same except for interrupts, a lot of the interrupt stuff creeps into these diagrams. Here's what a read looks like. Here's what a write looks like. Here's what the hold cycle looks like when memory grabs the bus and says, we can't have another clock yet. Here's read with a wait. This shows what read looks like if we apply the wait. Here's an interrupt, what happens if we have to do a hold. And then more data and a list of all the instructions. I'll give you a better list than this for us to go through in just a minute. So that's the data sheet for the processor. Just basically, it's another processor in Intel's line, and we'll place it into context when I give you a little bit of the history either later tonight or next class on where this processor came from, because it's where the SAP and its line kind of converge with Intel. And from that point on, there are no SAP computers. They're not simple as possible anymore. Now they are actual, really, you can do work with them. We saw that we could do some simple things with the SAP2, but the SAP3, even without interrupts, is a real computer. And certainly by the time it's an 8085, it is. Okay, let me close that. Minimize that. What is that window? I don't think that's anything. Let us download. I think that's what it's called. Try that and tell me if that works. Okay, everybody get a copy of that downloaded, unzip it. And then when you get it, you'll see you have in there the model, you have a picture of the chip, and you have the instruction set. We're going to go over the instruction set next, so you can get that open and big enough to see. Okay, I'm assuming everybody got that. Where did that go? Okay, I'm going to go to page 1 again. Let's do this here now. Oh, here I am. I'm on page 1. Okay, now I've marked some interesting things for my own use, but I've also circled some, and as we go along, I'll tell you when they're not part of the SAP3. We'll assume they're in unless I tell you they're out, in which case they're on the 8085, but not the SAP3. We have a new instruction, as I mentioned last time. Add with carry. Add with carry can take any of the registers, A, B, C, D, E, F, L, and N, well, A, B, C, D, H, and L, and it can take a register called M. So I didn't see on that picture anywhere an M register. Okay, does anybody see the M register? Just verifying your copy and my copy are the same. Yeah, no, there isn't one. But here's the deal with this. Remember how if we crunch 2 registers together, we would get a register whose name is the thing that's on the first side here. And its value was whatever the contents are inside those registers. I think we don't need that. So the H register down here can be pressed against L, and we get those 2 taken together, and we get a 16-bit number. Well, that's a 16-bit number. The instruction, the add with carry, needs an 8-bit number. So what M means is, anytime you see M, it means take whatever is in the HL pair, treat the number you get as a 16-bit address, go to that address, and get the 1 byte of data that's there. So it says use the HL pair as though it were an address. I mean, this could have been data, right? But it's saying specifically use it as an address. So let's say at the moment, H has a 1, 2, L has a 3, 4 in it. Let's say the accumulator has the number 2 in it. Somebody gives us an instruction that says add with carry. Actually, I can probably type that. Add with carry A. So what's A going to contain when that's done? Well, what's in A? There's a 2. So take a 2 and add it to a 2, you get a 4. So when we're done, the accumulator contains the number 4. Now somebody writes, add to carry H. The H character contains a 1, 2. So we add 1, 2, and 4. A now contains 1, 6. Now somebody says, add to carry M. When they say that, they're saying, go to the address 1, 2, 3, 4. Here's the address 1, 2, 3, 4. Find out whatever's there. There's a 1 there. Pick it up and add it to the accumulator. So 1 plus 16 means that now contains a 1, 7. Assuming I did my arithmetic right. So since this instruction is using 8 bits of data, it can use H, it can use L, they contain 8 bits of data. However, it can also get 8 bits from the place they taken together point. So if you treat them now as a 16-bit pointer, the data where they point is called M, and you can go get M. Let that soak in and bask over you a couple of minutes. A lot of people lose a lot of points on that one. So what is different about add with carry? Well, let's look at how the instruction works. It takes whatever's in A, I'm sorry, the second instruction, takes A, adds what's in A, plus the incoming carry to it. That'll give us the answer in the accumulator, and it will set the flags. How will the flags be set? Well, the sign flag will be set if it's turned on. The 0 flag will be set if the answer was a 0. If this forced a carry out, you'll get a carry flag turned on, and parity and the auxiliary carry will be set as well. We don't care much about them, but they are set. That's different than a regular add. This is a little different. A regular add, which is this line right here, does not take carry into consideration. So when you add up the first 2 numbers, they always have 0 coming in. Notice they do set carry, though, at the end of the operation, or 0 or plus, the sign flag. So we could use a regular add for the right-hand column of a 16-bit number and an ADC for the second column. We could add up 16-bit numbers. Now notice up here also, we still have our add with carry, just like we had down here somewhere, an add. This is the regular add, immediate. This is an add, but include carry, immediate. So these aren't particularly hard to grasp. The only thing is we now can use carry to our benefit if we need to. Any question about any of those 4 instructions? Here's AND with the accumulator, any of the registers, or the thing M points at. Remember, M is really H and L taken as a pair. And we have an AND immediate also. Answer goes in the accumulator. We have a call where the address is in the instruction. We have a call only if carry is set, meaning this call only happens if carry is set. We have a call if it's a minus number, meaning the Z flag is set, or the sign flag is set, not the Z, it's sign flag. So we have conditional calls. Complement the accumulator. Nice shoes. Complement carry. If we want to change carry from whatever it is and have it change all by itself, we can just use the complement carry instruction. Notice we also are being given the number T states, what flags are set, and kind of this is kind of what the operation does in kind of very abbreviated form. Now we have compares of all types. We can compare what's in the accumulator to what's in a register, or in the one case down here, what's wherever M points, and M is really H and L taken together. Now, I'll give you a little secret here that not many people know. Compare is really the subtract instruction. It just throws away the answer. Literally inside the chip, they run the subtract instruction, which sets the flags, which is what compare needs to do. And then when they're done, instead of changing the accumulator, they leave it be to what it used to be. Now here's another one of these type of instructions where we can go somewhere based conditionally. We can call something if not carry, so if carry is not set. We can call something if carry is not 0. These are a little tricky here because of the P. We can call, in this case, if it's a plus number. We can call here if the parity is even, or the parity is odd. Oh, no, I'm sorry, it's not. Which one is this? CP. Oh, this is compare. Where is compare? We don't have compare odd, do we? Yeah, we do. It's just listed lower. So here's compare of odd. This guy is an immediate operand. We do the compare with a byte in memory against the accumulator. Again, it's really just a subtract immediate, but we throw away the answer. And finally, we have another one of the calls, a call if 0. So those you can kind of go through. It's very rare to use a call other than regular call because its programming style doesn't normally dictate it. But compilers will generate these other ones as optimization so they don't have to put an if statement in front of the call. This instruction only exists on the 8085. It's not on the SAP3. It's called a decimal adjust after addition. What it does is it assumes that the accumulator contains a binary coded decimal number. And all it does is fix it so that it has the correct value in it and is still a binary coded decimal number. So, you know, if I somehow manage to get that number in my register, you know, I was probably adding something to a 9 or something, and it gave me that. What it's going to do is it's going to fix the number. It's going to bring the second number there down under 10, and it's going to carry whatever is necessary to make the left number correct. This, and there's one that's like it. Did I write down the name of it? DAS, which is the decimal adjust after subtraction, which lets you do the binary coded decimal instruction. Remember, I told you that the 8085 can do those. These are the only two instructions it can do. But it fixes up what you're doing in binary coded decimal so that you can continue working in binary coded decimal if you need to be. And there's good reasons to do it, because it's a lot easier to convert to ASCII from a binary coded decimal number, because you just simply, as a number, slap a 3 in front of the number you have. And, you know, that will fix you with a base 16 type of hex value. Okay, moving ahead, we have some DAD instructions. DAD stands for double add. Now, this is an interesting one. You know how every time I set up here, M could be used because H and L contain values that are used as this address. What happens if we have a program and we really would like to use the pair that's in B or the pair that's in D? Well, DAD uses as its accumulator the HL pair. So if I were to say DAD B, and B contain 1, 2, 3, 4, it's going to take 1, 2, 3, 4 and add it to whatever HL already contains. Let's assume HL contains 1, 1, 2, 2. And when it's done, it would contain what, 2, 3, 5, 6, or whatever I wrote down there. This number now is put in the HL pair. So when we're working with double length numbers, well, actually, this is the double part of it here, the first D, then we're going to have to have an accumulator, and the accumulator won't fit in the A register, so the default register is the HL pair. So by doing this, we're able to manipulate more than one 16-bit address at a time. That could be really handy if we were copying from one place in memory to another and we needed both addresses. Now, we never have two addresses in the same instruction. If you have data in an instruction, it'll only be one time in memory. The other time will either be inferred in a register or it will be part of the instruction itself. You'll never go in memory to two places to get data. But between and among multiple instructions, you might need two addresses. So let's continue on to the next page. We can also use the DAD instruction with the stack pointer, meaning we can take what's in the stack pointer and make it be the contents of the HL pair. We would have to have a special reason for that, and if we were writing an operating system or a compiler, we would certainly be able to come up with one. But for our purposes, it's just a novelty to know and tell. We can decrement all of the registers, including the one that is really a memory byte pointed to by the HL pair called M. We can also decrement the register pairs, B, D, H, and the stack pointer. So this would be, you decrement the B and C register as a 16-bit number, meaning it will handle the borrow between the third and the fourth bits right in the middle. The D and the E register, the H and the L, or the 16-bit stack pointer. That could be handy if you have a 16-bit number you're working with an address and you need to do some sort of computation that involves making it smaller by 1. DI and EI are not available on the SAP3, but they are available on the 8085. They're used for disabling interrupts and enabling interrupts. And since we're not going to focus on interrupts on this processor, we'll just leave it be that they use that interrupt register I was talking about earlier. And anything that can be masked, they have bits that can be set to allow that event to be masked. Halt. We can tell we derived ourselves from the SAP2 because it's still 76. We have an end instruction. We know about end. This byte can be from 0 to 256. It's up to us to make sure that whatever's hooked to it either is an in if we want to do an in, an out if we want to do an out, or it's one of the other and we've externally switched it to the correct mode before doing the in instruction. This would work with 00 and 01 just like it did on the SAP2 if we wanted to implement the same sort of a keyboard. Here's the ability to increment an 8-bit value, including one that might be in memory. And again, here's if you wanted to increment a 16-bit item, you could do it using one of these 4 instructions. Now we have a bunch of conditional jump instructions and one that's not conditional. Jump if carry, jump if minus, meaning a negative number is set. Jump always, this is unconditional go to. Jump if it's not carry. Jump if it's not 0. Again, watch your P's here. This is jump if plus. This is jump if parity even. Jump if parity odd. Jump if 0. Here's our friend, the old load accumulator. We put the address in the instruction. It goes to that number and picks up the value. This is one of the ones that gets things out of memory for us. Now, here's some instructions. None of the 3 of these are on the SAP3. LDAX is load the accumulator extended, meaning basically you're going to load the accumulator wherever the BC pair point. They're treated kind of like H and L in this instruction. This one, load the accumulator wherever D point. We don't need to use H because we already have an instruction that'll do that. But these are specialized instructions that extend the abilities of the BC pair and the DE pair in order to load the byte they point at. Now this one allows us to take an address that's hardwired in the instruction and stick it in the HL pair. So if we just wanted to initialize HL to an address, this instruction will do that. The next 4 are the immediate load extendeds. So here's a double address, double address, double address, double address. It picks that value in the instruction up and puts it into the pair. So BC will be equal to whatever those are. D will be equal to whatever that is. H will be equal to whatever that is, and the stack pointer would become equal to that. Now you say you want to buy a bunch of move instructions, huh? Well, look at this page. We got it several. And before we look at them in detail, look at the next page. Oh my goodness. And the start of the next page. Do we have a lot of move instructions? Holy mackerel. Move from the one on the right into the one on the left. They do it for all the registers, and they do it for wherever HL points. So we can put the into the accumulator whatever's pointed to by the HL pair. Same thing with B, C, D, E. We go through all of them. Everything will be there that we expect to be there except for one of them. Can you imagine which one is missing? Robert?
The flag register.
Well, that's not one of the registers you move anyway. Scott?
Move M to M.
That's exactly right. Because in that case, we would be moving something from memory to another place in memory. So if we go down here, there is no move MM instruction. But this is interesting because the last instructions, we're moving from right to left, allow us to move data into memory located wherever H and L point. Don't forget about that these instructions. This last set of moves are very powerful. They're almost like a store instruction, whereas all the others have been almost like a load instruction. Move immediates with all the obvious places. Notice the last one has 2 memory locations, but it's okay when the memory location is inside the instruction because we got it when we picked up the instruction anyway. It doesn't need special memory processing. No op still does nothing. OR works like the AND, except it does the OR function, and there's an immediate form of it. We have an out. Again, 00 through FF are legal bytes. It's up to us to make sure we're going in the right direction, though, when we get there. Unfortunately, the pickle instruction is not on this machine. You guys just like saying pickle. All this does is it takes the contents of H and L and it puts them into the program counter. Whatever's in H and L can go in the program counter, meaning we can compute where the next instruction is. The reason it's not here is because that has been learned over the years not to necessarily, unless you just don't have an instruction that'll do it, to be a particularly good thing to do. But hey, everybody likes pickles, so we can use it on the 8085. We can pop BC, pop DE, pop HL. Notice these all have to be 16 bits so that they can be popped. We can also pop the program status word, which is the A register followed by the F register. And we can do the same thing with pushes. We can take the B and put it on the stack. We'll always put it on the top of the stack, and it'll make the stack grow by 2 bytes because each of these are 16-bit pushes. Now, I'm going to go through these quickly and then come back to 4 of them. We'll come back to RAL, come back to RAR. This is return conditionally, meaning return if the carry bit is set. Unconditional return. We'll come back to the RIM as well. RM is return if minus, return if no carry, return if not 0, return if positive, return parity even, return parity odd. Now the RIM is not on the 8085, and it says basically read the interrupt mask. Since we don't have the interrupt register or interrupts, we don't care, but that's what it does. It gets it so the other instructions we saw that could operate on those bits could use them. You could get what the current values are. We're going to see the opposite of that in a few minutes, which is called the, what was it called? The SIM, I believe. See if I wrote it down anywhere. Yeah, SIM. And it stands for set interrupt mask. We haven't gotten to it yet, but we will. Now, here's the confusing part. We already know what RAL and RAR are, correct? Well, RLC, and is it RLC? I'm going to confuse myself here very shortly. Yeah, RLC and RRC are also rotate instructions. Now, amazingly, and I'm not sure this sheet matches the correct answer to this, but RLC and RRC, this guy and this guy, are the same as the SAP2, RAL and RAR, meaning they're 8-bit rotates. These two, which have the same names as the SAP2 instructions, don't work that way. Instead, these are 9-bit rotates. When the 8th bit falls out, before it goes back in the other end, it falls into carry. And there's some operations you can do where 9-bit rotates are much better than 8-bit rotates. So if you were to look at it, that means that SAP2 programs can't run because those two instructions are different. Now, in real life, and if you look at the notes over here, they fix the problem. These match exactly what the SAP2 does, and the other two are the 9-bit ones through carry. That's the definition we will use no matter what you read elsewhere. So these work exactly like they did on the SAP2. But if you look over here, the other two rotates, these have been fixed to say they go through carry or with carry. So notice they don't set carry because they automatically pass through it. It automatically becomes set. So that little confusion out of the way. We have 8 RST instructions. We do not have them on the SAP3. RST, whatever the number is, stands for reset. Actually, it stands for, did I say restart? It's restart, not reset, restart. The reason is because all of these can be used for software interrupts. There are vectors down in low memory that I showed you in the picture earlier that if you call an RST3, there's a vector down there waiting for you to execute. It is just simply a jump to library code or your code, whichever you have, that knows how to execute whatever you define an RST3 to do. Generally, they're associated with input-output, but they don't have to be. Software interrupts are very powerful on more powerful machines because they also can allow you to change whether you're operating in supervisor or in normal mode. In our case, we're just going to ignore them and be aware that they exist on the processor. Over on the right-hand side, though, you'll see where the restart occurs. Notice that the first restart starts exactly where your program's reset vector is. So if you want to run your program a second time, you can just force that interrupt to occur. It'll jump back to the start and start all over again. Each of these places probably just simply have a jump somewhere else where the program code really is. And one more return left over, return if 0. Now, as we might expect, we have all the subtracts we could possibly want, including the SUI, which is a subtract immediate. And we have subtracts with borrow. These take into consideration whether carry is set or not, because borrow is really just carry kind of inverted. And if you think about that, when you're subtracting numbers, if the smaller number is on top, you have to borrow one from the column to the left. We can't do that with just a subtract instruction because there's nothing to borrow. But with this, it gives us the ability to take away an extra carry if it's set. Here's a whole bunch of instructions that don't exist on the SAP3. The SHLD instruction, and if you look on the left-hand side, what it's really doing, it's taking and it's storing the H and L pair in memory. And it's storing it wherever H and L used to point. We said we'd see sim eventually. Here it is. Here we can take and load the HL pair into the stack pointer. Remember pickle? Well, spickle here is like pickle, except this is another one that's not allowed, but it just simply takes HL and puts it into the stack pointer. The two stacks instruction, one will store the accumulator extended type of a thing. So the accumulator extended here is going to be M. If we look over here, you're going to take the accumulator and store it wherever BC points. In this guy, we're going to store it where DE points, very much like the low LDX instructions, which did the opposite. But we can use BC and DE as a pair if we use these instructions. Again, we don't need M because we already have instructions that do the same thing. Here's a way for us to set carry. If we just need to turn it on and we don't want to do anything to force it on, we can set it on here. Remember, clear carry was another one we had very early on in the instruction set. Here's all the subtracts. Here's the ability to exchange the DE pair with the HL pair. It's not available on the SAP3. Then we have the XOR instruction, all of its flavors, including an immediate. And finally, we have one that's only on the 8085. It's not on the SAP3. And if you notice, it does an interesting thing. It goes to the stack, and without popping the stack, it copies the top two members into the HL pair. So it just grabs the top two things on the stack without removing them. It's like a peek instruction almost that peeks and puts it into the HL pair, where you could immediately use it as an address if you knew it was an address. Again, that's very useful with interrupts and with the 8085. Not so useful for us with the SAP3. Anybody have any questions about any of the instructions in this instruction set? It's fairly powerful. We fixed some of the limitations, and then we've also fixed some of the things that were in the SAP3. Don't underestimate the SAP3, though. Without interrupts and without some of the pointer fancy business, we can do an awful lot because we have enough of the pointer business that we really can use the registers. We just may take more instructions to do things than we would have on the 8085. No questions at all. Scott?
What's the purpose of ANDing A with itself? And I guess the analogs for the other registers.
Well, let's just take any of them here. You're talking about AND?
Sure.
Okay. Where are their ANDs? Here they all are. If we take and we just do the AND function, the first guy, what happens if you AND two values against each other? What do you get for a result?
It's going to give you either a FF or a 0. I got it.
Well, let's take and work, make sure everybody understands what you're saying here. So I've got this register in the accumulator. Now I want to AND that with itself. Where will the ones be in the next row? Well, everywhere there's two ones, we'll get a 1. Notice we didn't damage the register at all. But also notice one of the things we would have done, where's the AND? Here it is. We would have been able to set the flags. So if we had done nothing, we wanted to keep what's in the accumulator and we need the flags to be set. One of the things you could do is AND something with itself. That make sense, Scott?
Yeah, that makes sense. Yeah.
And that's not necessarily the best answer. I mean, there could be other instructions which are better, but because of the way they encoded the instruction, it was just as easy for them to give it to you as it was to try to take it away. Mikhail, you have a question?
So with all the new instructions we have, is multiplication and division still carried out in the same way?
Well, there is no multiply and there is no divide instruction. So if you're going to do either one of those, you'd have to come up with your own algorithm for doing it.
Yeah.
You notice there's nothing in here that's built in that does multiplication. On an 8085 processor, they have the ability to use a coprocessor through the input-output system. And when they do that, they can do the multiplication and division over there, but we don't have one of those. The one we have can really do a lot of logic, and it can do adds and subtracts, but that's about it. Robert?
So kind of along the same lines of Scott, we have a move A to A function, and it doesn't set any flags. So what would be a potential purpose for that?
Well, I can think of a couple. But let's look at it over here so we can take a look at what's happening. Okay, when you do a move to A, just the contents of A are copied into the accumulator. We know that A at the end is going to wind up exactly like it was, and then nothing's going to happen. Nothing extra is going to happen. The two things that you have in terms of why it's there is when they wanted to guarantee symmetry for the thing. They themselves were quite disappointed when they noticed you couldn't do the MM combination. But giving you that doesn't hurt anything. And it gives me a harmless instruction if I ever need to burn 4 T states in a delay function. I can do one of those and it won't hurt anything. Now, there's other instructions that'll work that way too. But in terms of how they encoded all of the opcodes, they had an extra spot, and it was symmetrical if they went ahead and encoded this. So they just did. Any other questions? Those have been good questions. If you got others, ask them. Actually, let's do this. I'll do that. Do that. I want to add those two numbers up. Add the number here and the number here. Notice I have shortened it down to 4-bit registers instead of 8 bits. We'll forget about the leading ones in this case, zeros in this case. We're going to pretend like they're just 4-bit registers to illustrate a point. I don't want to have to type all the zeros. You've seen me type. So I want to add BC to DE. If I were to write an instruction to do that, I wanted to add these two together first. What would my instruction look like to make that happen? I'm going to, first of all, I got to get something into the accumulator because we're always adding to the accumulator. Is that right? Back at our adds. So add always winds up in the accumulator. So let's say we take C and put it in the accumulator. What instruction would I use to do that? Miguel?
Add C.
I just want to get C in the accumulator. We don't know what's there right now. Patricia?
You move C to accumulator.
Yeah. Okay. Now we want to add those two together. The E to C, right? So I could say add. Where's my answer going to wind up? In the accumulator. So C and E. Now where is my answer at this point? Scott?
We got all zeros in the accumulator.
That's right. So the accumulator right now contains all zeros. How about what do the flags have in them right now? When we look over here, it sets the flags. So that means carry is set, right? So we have 0 in there, we have carry set. So now we want to do a similar thing. First thing we probably want to do is stick this number somewhere. Why don't we stick it down in the HL pair? So how do I get it into the L register? Move something to L, and something is the accumulator, right? So now I've got to get what's in the B register into the accumulator so I can add what's in the D register to it. So I'll use the same technique we did last time here. We're just going to move to the accumulator, whatever's in the, I think we said B register this time. And then I can do an add to the accumulator of D. And then if I wanted to store that in the HL pair, I could just do that. So now the HL pair contains the answer, except the answer is wrong. Robert, what's wrong?
We need to add the carry bit back in.
We do, and we didn't do that, did we?
No, we did not.
So how do we do that?
Well, we're going to add it to, which was the higher order pair was B. So we would add the carry bit to B before we added D.
Well,
or after we added
yeah.
D was fine.
Why don't we just use the instruction called add with carry?
I mean, we could do that too.
Because that's what we want to do, is we want carry to be considered in the sum. So stringing these together and getting rid of the extra fluff and extending them out to 8 bits, we'd have a 16-bit answer where the carry would have worked across the middle of it. So in general, if you have two numbers added together, or 3 or 4 or 5, let's say we were going to add that number to that number, we're really going to do it in pairs. We'll add those two together and get an answer, and the carry bit will be set or not set. But this guy didn't care about carry, so we just use the regular add instruction on him. These guys, though, care about carry because he might be giving them a carry, he might not. So when we add these two up, we use the add with carry instruction. If this had been longer, all the next sets of columns we'd add would use the add with carry instruction, only the rightmost one. If you think back to hardware, what did we call this type of add? It had a name. Now, there's got to be more people in this room than Robert and Scott. Remember, things from the first part of the class don't go away on the next exam. They're going to be emphasized. I guess I have to go to one of you guys. Robert, why don't you tell me?
It'd be a half adder.
That's a half adder, yes. What's an ADC then, Scott?
It's a full adder.
Exactly. You guys are so brilliant. Okay, so we've just basically proven what in hardware also works in software. That's a good thing. Now, there really is very little to tell you about this instruction set if you can run your eyeballs down it and not get sidetracked by trying to understand the instructions we're not using. Most of these are pretty well explained over here, although they're kind of tersely explained. And you have to watch your M's occasionally, like where they say HL here. You have to make sure you know which M they're talking about, because see if we have there's another case somewhere close by here. Yeah, this guy. Here's the H. Well, these are both HL. Here's a BC. Here's a DE. So you have to make sure which M they're talking about. Remember, M is simply the data that's pointed to by that pair of registers. Now, did I save that picture? I didn't. Oh, well. Maybe it's on the whiteboard. No. When I mapped out memory for us, I said up at the top up here is where we initially set the stack pointer. When we do a reset, not a restart, but a reset, the stack pointer is set to zeros. That means it points one past the end address. The last address up here is FFFF. Do we need to adjust it in order to do a push? Let's say we were going to do push B. Is that a stack pointer okay, or do I need to do something special with it before we can start? Well, when we do our push, the first piece of data has to go at FFFF, and the second piece has to go at FFFE. When you're initially starting, that's where the first stack, this is the top of the stack right now at 0. So there is a way to make it work. If the hardware moves the stack pointer before it moves the first 8-bit piece of data, which would be the B register, then it moves it again and puts the C register. Then we would have, after this has been done, the B register in here, the A register here. This would be decremented twice, which means it would point right here, which is the next place we're going to put data. On the other hand, if the stack pointer initially points at FFFF, then we put the data before we advance the stack pointer. So we put the data, we advance the stack pointer, we put the data, We advance the stack pointer, and the stack pointer in this case always points at the next available empty bucket. The truth of the matter is the SAP1 or SAP3 uses this technique. You'd have to read the data sheet to find out which one the 8085 does. And we will have to run an experiment when we get our AT Mega 328Ps out to see which it does. So both of those are ways that stacks can be maintained. We have no way of knowing, you will have no way of knowing because you can't run this processor. I didn't give you a simulator for it. You might find it in the data document. Maybe, maybe not. Well, you'd have to read it carefully to see. But the stack pointer here on the SAP3 is defined to be set initially by reset to zeros, which means it always has to be moved before data is stored. Moved again and data is stored. For every push or pop, 2 addresses are used up. For every call or return, 2 addresses are used up. Anybody have any questions? Okay, I would suggest very, very strongly that judging on your participation, you don't know anything. So I would use this weekend to get myself up to speed on the material we've been covering over the past couple of weeks so that we'll be able to get you through that exam. You don't want to fail this exam. I mean, the homework may have already gotten you, but the participation may have gotten you. But try to pass the class if you want to learn this material. I don't know why you wouldn't. This is wonderful stuff. So I will see you people, I guess, on, what is today? Today's Wednesday, so I'll see you on Monday night. And don't forget, next Wednesday night is the exam. So be ready. And other than looking over your notes and studying, I suggest you spend your time doing that between now and then. Any last words before you say goodbye? Okay, then goodbye.